In this fourth video lecture of this unit, fourth and second to last, we're going to discuss convergence in LP and how it also gives convergence in expectation. And let us start with this simple observation. It says if a sequence of functions converges in LP, then they also converge in measure. So this proposition is true on any measure space. It doesn't need to be a probability space. It doesn't need to be sigma finite or finite. It says if a sequence of Borel functions converges to another Borel function in LP for some p between 1 larger than 1 and finite, then these functions, they converge in measure as well. And now let us see the proof of this proposition. It is very simple. Assuming we have convergence in LP for some p larger than 1, this means exactly that this integral converges to 0. The integral of the difference between fn and f, the absolute value of it, to the power p. But now we can use Chebyshev's inequality or with the pth power, the pth moment, to say that for every epsilon positive, the measure of the points omega where the difference between these two functions is more than epsilon, we can bound it from above by, as we know, epsilon to the p times the integral on omega of the difference to the power p. And by assumption, because if n converges to f in LP, this integral will converge to 0 for every epsilon fixed. It doesn't matter how small epsilon is. Of course, if epsilon is small, this fraction here becomes large, but epsilon is fixed. And for each epsilon fixed, n is being sent to infinity. That's the definition of convergence in measure. So Fn will converge in measure to f, which is what the proposition says. The next implication that we have is if Q is larger than P, then convergence in LQ will imply convergence in LP. That doesn't sound quite right, because in the last unit, we saw examples of functions that did converge in L2 but not in L1, and another example that did converge in L1 but not L2. So there is something wrong here. There is something strange. Yes, there is something strange. What is new here now is that this is true only for probability spaces, not for measure spaces in general. For probability spaces, the largest P, the hardest it is to converge in LP. Or said differently, if a sequence of random variables converge in LQ, then it will converge in LP for a smaller p. And how can we prove this proposition? The proof goes as follows. We focus here on this. This is the proof. So, and this is the inequality that is something that needs to be justified. The assumption is that this expectation of xn minus x to the power q, it converges to 0. Well, since it converges to 0, we can raise it to any positive power. It won't matter. It will still converge to 0. So the part of the proof that where we'll spend most of the time justifying is this part here. This part which says the expectation of y to the p to the power 1 over p is bounded from above by the expectation of y to the q to the power 1 over q. And this will give us, as a particular case, an exercise that we did already in a previous unit, which says the expectation of x is bounded by the expectation of x squared square root. This is just the case when we take p equal 1 and q equal 2. So back to our proof. what we need is to show this inequality here for any random variable y. And to prove this, to justify this, I'll take y, let y to be any non-negative random variable, which means I'm writing y here for what here is absolute value of y. And we have to show this without the absolute value. And we're going to do this by using Jensen's inequality. But before we get there, Jensen's inequality is for integrable random variables. So we need to take some small detour in order to make it work. And this detour will be the following. Take a sequence Zn of random variables which are integrable and which increase to y to the power p. Of course, this is always possible. We know any non-negative function can be approximated from below by simple functions, and simple functions, they are integrable as long as they're not taking value infinite. Another way to approximate is let's take z to be the minimum between y and n and raise that minimum to the power p. So whenever y is larger than n, we'll take n instead of y. So this is one way to take such a sequence. It doesn't really matter what particular sequence we take. It needs to be integrable and increase, non-decreasing, and converge to y to the power p. We want them to be integrable because now we're going to use Jensen's inequality with the following function f of x that maps x to the power of q over p. Q over p is larger than 1, so we can compute f prime of x. It will be q over p to the power x q over p minus 1, which is still positive. So this is increasing. This is still increasing on r plus. And well, when the derivative is increasing, then the function is convex. And now, yes, we can finally use for these variables at n, which are integrable, we can use Jensen's inequality and say, well, the expectation of these variables Zn to the power q over p are bounded by the expectation of Zn to the power q over p. So what did we change here? Well, before q over p was outside the expectation, and now q over p is inside the expectation, and therefore, and this is exactly Jensen's inequality. Jensen's inequality is exactly saying f of the expectation of z is bounded by the expectation of f of z. So this is exactly Jensen's inequality. And then finally, because Zn here, Zn is bounded from above by y to the p, we can substitute here Zn by y to the p, then p over p will cancel, and then we get simply y to the q. So we have this inequality for every n, but now we can take the limit in n. Why can we take the limit in n? Well, we have this inequality. We can take the limit in n by monotone convergence theorem because we assume that n is increasing and increasing to y to the power p. And when we take now the limit here, we get e to expectation of y to the power p. So what we got is expectation of y to the power p to the power q over p bounded from above. Now I'm copying from here, expectation of y to the power q. And now we can raise both sides of this equation to the power 1 over q. And this becomes exactly what we had to show, which is exactly the equation we had to prove here.